Thanks, Krishnendra, Pooja, and Praveen. So, yeah, this class was supposed to be held on weekends, but I had to take it today because uh, these weekends I have other commitments and we need to finish this course as well. So, and also I'm happy that I'm not taking up your weekend, but some of you might have office or classes today, due to which you might not be able to attend. So, you'll have the recordings with you and all the scripts, everything is there. So you can go through the recordings, you can go through the documented script. Everything should be fine. And yeah, this is the last class to this course on antenna design and simulation with MATLAB. This is the fourth class. We in the previous three classes we covered MIMO antenna. Sorry, we covered dipole antenna, some other antennas, loop, microstrip, slot, horn, patch, and everything. And yeah, there are feedbacks. I went through them, and I request everybody to fill up the feedback form, especially if you want a certificate for the completion of this course participation for this course. So make sure you fill up the feedback form. Otherwise, and the deadline is tomorrow. If you do not fill up the form, I'm sorry, I could not be able to provide you with a certificate. And make sure you go through the lectures and run all the scripts that I've provided, um, and go through them as much as you can. If you go through a couple of them, then rest of them will look very familiar because um, the EM simulation part scripts are very, less in them. Most of them is about how to plot, how to put markers, and how to label things. The EM part is very small, like just for calling functions as parameters, pattern, azimuth pattern, show for the antenna structure, like that. And in the first class, there was a request to do MIMO antenna simulations. So I decided I'll include that, although um, there is a lot of material to be covered today. So we'll go through everything quickly. In MIMO antenna simulation in MATLAB is sort of a derivative from the an array simulation. So we use the same class, antenna, the linear array, rectangular array, conformal array, and then from that itself we can do MIMO simulations and get the S parameters and then evaluate other MIMO metrics. And I'll quickly show the GUI today. We won't spend much time on the GUI because we have to cover planar arrays, some frisk transmission, which I thought I should show everybody just in case if you want to do some a different kind of analysis, the effect of you know uh, distance and polarization. So I'll show that as well. So continuing the previous lecture on arrays, we'll finish planar arrays today. And again, we'll see broadside and fire and phase. We'll see one code for planar array for different for broadside and end fire, and then a filtered 45-degree phase. So the goals is to learn 2D planar arrays, and we'll see some other examples for which we won't discuss the script. I've shared the script with you. They're very similar to the one which I'm showing here. And then we'll see steering and progressive phase shift. So, what is a planar array? It's a in the previous class we saw a linear array in which all the elements are in one line, and then they are arranged in some with some d spacing. So naturally, if we so this was, for example, just in the x direction, and we had z directed dipoles. But if what if we repeat this structure along y-axis? In that case, we'll end up with a with an arrangement looking like this. This is an example of a planar planar antenna array where we have antennas in one plane. You can always be more creative and then arrange them in 3D space as well. So this is to illustrate that you have the freedom of geometry. So and for in MATLAB you can do a planar array by using the rectangular array function. But if you want to do a more creative geometry, for example, if you want a certain number of dipoles in one plane and then some others at a different height, then you have to, use a conformal array. But if you want to do a planar array, there is a function which just takes in the element and the spacing between them and the phase between them, and then that will just automatically create all this, and then you can study the effects. So instead of one antenna, we use many antennas arranged in a grid, and this is an example of the arrangement if you see it from the top. So this will all be in one plane. And advantages are like if you have one antenna, you will have a certain gain. If you have like if you have a 1D array, your gain will increase. And if you have a 2D array, and if you give phase and amplitudes correctly, gain will increase further. And then you can have directional beams and electronic beam steering and more degrees of freedom. For example, if you had a planar array, then it could steer in one particular plane in one direction. But if you have a 2D array, then you have the freedom to steer it in all directions in this hemisphere. We'll go through four different cases. I'll first show you the result, then run the code for you, and then we'll go through the script. So the first case is the broadside array. And one thing you'll notice in all the four cases, geometry will remain the same. And what will happen? It will change the phase excitation of each dipole. Uh, and then the pattern will change. So we'll see in the script how we create this dipole planar array, and then we'll change the excitation by using these expressions. So each dipole will be excited by using a phase phi, which is given by m beta x and plus n beta y, given that the dipoles are arranged in the xy plane, and m and n are the indices for uh, m is for the x-axis, so 1, 2, 3, 4, like this up to 8 values, 1 to 8 values of m, and similarly for n, 1 to 8 values. And this will create, we'll have a mesh for and the first dipole will be at 1 comma 1, and the last dipole will be at 8 comma 8, and for example this dipole will be at 1 comma 8, and this dipole will be at 8 comma 1, like this. Okay, so we'll have a mesh, and m and n will give the location of the dipole, and beta x and beta y will give the phase based on the tilt that we want, and this phase will be then given to each dipole. So from this combination, we'll have the phase for each dipole at phi m comma n, and we'll also and the script also plots the phase plots. So in this the first case, although this looks like we have a lot of phase change happening over here, and it's overwritten over here, but this is it into 10 power minus 14. Okay, so all these values are actually very close to zero. So in this case, this should all be red. Okay. So just ignore the first case. This should all be red. This is very minor difference that it hence uh, MATLAB has done this. So this is all red, and all of them are at the same phase. And when they are all at the same phase, we have broadside radiation because all of these the radiation from all these dipoles add up constructively in the normal direction of the plane. And it's visible over here. And the plane is arranged like this, and we have all the maximum radiation in the broadside direction. In the next case, we have the end fire along x direction. So in this case, You can see the phases over here. When if you go through the formula, and this will the beta x becomes minus pi, which is minus 180. Yeah, minus pi. And if you calculate it in degrees, this will become minus 180 degrees. And we will have the first row as at, let's say, 0 degree. The second row will be at minus 180 degree. The third row will be at minus 360 degree, and so on. So this is 90 degree. This is 90 degree. This is minus 180 degree. This is minus 360 degree. This is minus 4 540 degrees, and so on. Yeah. So each we have progressive phase shifts along the rows, and this will lead to an end fire radiation, as shown, as can be seen over here. Next, for then we can have an end fire y direction. So instead of having phase shifts like this, we can have phase shift like this. So the first row at 90 degree, then next at 180 degree, then next at 360 degree, and so on. In this case, the radiation, instead of happening in the x direction, it will happen in the y direction. Right. And similarly, if you want a tilted 45-degree case, so in that case, you can have 90 degree over here, 360 over here, uh, 540 over here, and so on. And this will repeat. So in this case, the beam tilt will happen at 45 degrees on the broad side. So you just need to place the elevation and azimuth angle over here for beta and x and y, and this will give you expression. And dx and dy are the spacing between the antenna elements. Right. So this is how we control the phase, the direction of the beam by controlling the phase excitation of each element. More on how to tilt the beam, how to do a phased array. You should refer to a lecture on designing phased arrays. Over here, we'll look at the implementation. Next, so we'll start with the script. Let me first run the script for you. We are doing dipole array. So here's the script. I've shared the script with everyone. This the script is well documented now. So it will show you uh, the purpose of the script on the top, and the elevation angles. Let's say if you have something, if for broadside, you'll have elevation 90, and elevation 0 is in the XY plane, azimuth is 0 is equals at plus x, and azimuth 90 at plus y. The orientation of the dipoles are in z, and the z direction. We have the maximum in the XY plane and null along the z. So things are documented, and this particular script will solve for 4 different cases. And as usual, you set it up, you give the number of elements in the n cross n array. For example, in this particular script, we do an 8 cross 8 array, and then you start with the parameters. Then there is the element and array builder. You define an element, and then you build the array under different cases. And then there's a function which maps out the phase, because you have to give excitation for each element, and so we do that separately. We give we make a matrix or mesh of the phases for each element, and and then we solve it using using for loop for each case. First case, second case, third case, and fourth case. We calculate for different cases for each case. Then this calculate gets the phase values, the bx and the beta x and beta y values just to plot. And then we build an array. We show the array, and we show the phase map, and then we calculate the pattern for each case. Let me run this. As soon as it starts running, you'll see case one being solved. We'll compute 3D pattern. So this should take a minute or so, maybe 2 minutes on a 16 GB system, something like that. You can see case four is being solved, so it's pretty quick. All the four cases are completed and the plots are being generated. So all the plots are generated now. Let me start from case one. This is the antenna arrangement, which remains same in all the four cases. So if I compare all the antenna arrangements, the four cases, yeah, you can see it's the same in all the four cases. In all the four cases, and again, you can always rotate and view the arrangement of the dipole in the XY plane. Right. So this is the arrangement of the dipole. For the first case, this is the phase plot, which we saw. If you look at this, let me extend this. It's it's overlapping over here, but you can see there's minus 14 over here. So this phase difference is very small. So this is almost all at 0 degrees, and all at 0 degrees generates a broadside pattern. You can arrange, you can again rotate and see. Since all the dipoles had a null at the center, so we have a null at the center, but the radiation is maximum in the broadside. And you can see the as I rotate, it's on the broadside of the antenna pattern. And on the XY plane, the pattern is maximum on the broadside. Similarly, we have the this arrangement of the phase where we have negative 180-degree phase shift along each row, and this leads to a x-directed radiation pattern. The radiation is maximum in the x direction. Similarly, if we flip the phase of the arrays, we have maximum radiation in the y direction. Right. And finally, if we do a phase arrangement like this, we have maximum radiation along 45 degrees with respect to the broadside. You see, this is maximum in the 45-degree angle. So we'll go, so this is how the cases, and in all the cases, the geometry will remain same. We'll just keep changing the phase of the elements, and that will give us different radiation patterns in different directions. And so the each element in this case is a lambda by 2 half wave dipole. The orientation is z directed, and I'll show you results for x and y directed as well. And I've given the scripts for these cases. We have already seen how to define a dipole. And in dipole, for example, if you create an antenna element A1 is equals to dipole, and then what you can do is A1 dot tilt. You can give the uh, tilt degrees, and then you can A1 dot tilt axis. You can give the axis around which you want the tilt. So you can tilt all the elements. So basically, since we are creating a rectangular array, if you just tilt one element, rectangular array will arrange the same thing for all the elements. So just the single element that you want to tilt. If you want to have some of them, all of them tilted, some or all of them tilted in different directions, then you will have to use conformal array, and then you'll need different types of elements which will be arranged in that. And the spacing we have maintained as lambda by 2. Since these are z-directed dipoles, lambda by 2 spacing is all right. But if all of them, if they were arranged in, x, in x, all of them were x directed. So in that case, if there is lambda by 2 spacing between the dipoles and both of them are also lambda by 2, then these dipoles would touch. So in that case, you have to make the spacing a little more than lambda by 2, and these all are arranged in the xy plane. And these are the four cases that we saw: the broad side, the x direction, y direction, and the tilted one. And the progressive phase shifts along the different elements gives you different radiation patterns. This is the formula for the phase excitation. You can refer to phased array lectures on how to design phased arrays. But once you know know what the phases that you want, you can this is the formula you might end up with, where you have the k is the wave number, dx is the spacing between the elements, cos of the elevation angle, and cos of the azimuthal angle. And so, for example, if your elevation is for broadside, your elevation is 90 degrees, azimuth angle is 0. So that gives you the broadside, and you just put in the value and you'll get the value of the beta x and beta y. So once you have defined, once you know your elevation and azimuth angle, and you know the direction in which you want the tilt, you can get your elevation and azimuth angle for that direction, and then substitute that those azimuth and elevation angle, the angle in which you want to tilt the beam into this expression, and you'll get the beta and beta x and beta y values. These are the phase steps, and these phase steps will then be used inside the array creation, and when you create the array for the different elements. So how to create the array, get the simulation parameter, get the how to create the array, and we will define the simulation parameters like usual we have done before. In this case, we have two spacing factors, dx and dy. If both of them are same, you can just use, say, d. But if you want to change, you can just change one of these, dx or dy, and see the effect, how that affects the pattern. And then we first create the element. Let's say we'll name the element as LM, and this is a dipole. And from here you can, if you change dipole to, let's say, loop, so this will become all loops. Okay. If you change it to PFA, this will all become PFA. If you make it patch, microstrip patch, this will all become patch. But the MOM solver of MATLAB is slow for dielectrics. So make sure if you are doing a path simulation, maybe try a 1 cross 2 before you go for higher, because this will be extremely slow. So we are defining a dipole of length and width lambda by 2 and lambda by 200, and making the element as LM. And then we're using a function to build the array. And what this does is, because we are solving it for different cases, right? We need to change the phases in different cases. Let's say if we had to just solve for one case, then we won't need this function. So we're just creating a function so that we don't have to write the script again and again. So even if you ignore the script for now, but let's say we just solve for one case, and we'll ignore the functions. Um, and what we'll do is we'll create the array as ARR, which is a rectangular array, because we want a rectangular array. If you want a different kind of array, maybe you can use a conformal over here. And then rectangular array takes the element whose array you want, the size in in a n cross n matrix. This could also be n cross m. We have chosen to have an 8 cross 8. It could be 8 cross 1 as well, or something 1 cross, and we can change the size. And then it takes the row spacing as dy and the column spacing as dx. And this creates the array of the element over here. And this array will have different parameters, and these are the important ones. The first one is the amplitude taper. So in our example, what we are doing is we are giving equal amplitude to all of the elements. So once creates uh, a matrix of n cross n size, and cross and size, and this assigns to the amplitude taper. So we're giving equal amplitude. And for the phase shift, ARR dot phase shift, so we're giving it as a phase grid. So in the next slide, we'll create a phase grid, which will be a 1 cross n vector. So, and this will map uh, the phases for all the elements. Right. So this is how we create the array. And since we are doing, we have to do, so in this case, we're solving it on 4 different cases. What we do is we run a for loop for each case. For case one, this will every time call a build array function. Let's say e case one is equals to build array. And then we'll pass on the arguments how we want to build the array, and that will give us the array in that case. So so what MATLAB and how you define a function in MATLAB is you name the function over here. You create an object which will be returned later, and then the function takes in different arguments. So the function will take the element as the argument, the number of elements that you want. For our case, we also want to pass the number of the size of the array as n cross n. So this is n, and then the spacing between the elements as dx and dy, and the phase values, because the function needs to create an array with phase excitation, so phase grid. Similarly, we need to create the phase map. So what we do is I've stated this earlier. So we each element has a phase defined by this expression phi at m comma n, and m and n are the row and column of the array, and m into beta x and n into beta y. Beta x and beta y is expression we have seen in the previous slide, and this will create the phase value. And this is to create the tilted wavefront. And if we put phase equal to 0 for all elements, we'll just get a broadside radiation. And in this script, what we do is we use a mesh grid function. This creates a mesh grid of in it starts from 0 to n minus 1, so it will create an n cross n mesh. And then for each element, we can get m into beta x and n into by, which is beta y, and this will give us the phase. So this is how we get the phase map. And in the script, this is how we'll write. So you must have seen in the previous when we were building the array, where we were using this object as phase degree inside the array. Uh, just give me a sec. Sorry about that. In the build array, we had seen when we created the object ARR, we gave it phase shift. Phase shift is equals to phase dot degree. And this is how we are defining the phase degree over here. So this is the phase map. And if you plot this phase map, this will look like this for different cases. So the phase degree is again made by a function called make phase. So we are making it as a function for so that we can call it for different cases. And make phase function takes in again the number of the size of the array, the wave number, the spacing between the elements, and the direction of the tilt. So for broad side, this is 0 and 90 degree. And for different tilt, for example, if you want a 45-degree tilt, then you have to send 45 degrees. So this takes the azimuth and elevation angle in degree. So first we can convert that into radians, degree to radian. We store the radian values. Then we calculate the beta x and beta y values by multiplying from the formula that we saw earlier, wave number times the spacing into the cos of the elevation angle, cos of the azimuth angle. And then for beta y, it's cos of the elevation angle and sine of the azimuth angle. We get the beta x and beta y values. We create the mesh grid and then multiply the m and n, the mesh grid values with beta x and beta y, and get the phase in radians. And then we again use a radian to degrees function to get the phase in degrees expression plot to get the phase in degrees as well. So we'll use the phase in degrees just for plotting, and we'll use the phase in radians to excite the antenna, because the array and most functions in MATLAB use radians while calculate while solving. So we built the array. We made a function which will build the array. We made a function which will build the phase map. And now we'll start the different cases and geometry for each case. So most of this script is to solve different cases in one script. If you want to just do one particular case, you won't have to write so much. You can just skip all the functions and do it sequentially. So but we are doing, we're writing a more complicated script just for demonstration and to understand what if we have to, solve different cases. So let's create an array or a matrix of the different cases that we want. And in these cases, this is how we are arranging it. So for this is the azimuth and elevation angles over here, and then the short label of what we want to do. We'll also use this for plot and the description. So for broadside we have 0 and 90, end fire we have 0 and 0. We have end fire in y direction we have 90 and 0, and for tilted we have 45 and 45, the elevation and azimuth angles. And this is a description. Broadside will have beam along z, end fire will have along y, sorry, end fire x and end fire y, and beam at 45 degrees. And once we have created the different cases, we'll count the number of cases. So a size will give us the number of cases. And over here we can see there are four cases. Uh, so this is counting the number of the size of this the matrix, and we have, you can see, one, two, three, four. So n cases becomes equal to 4. So and then we start the loop. So IC is the is our variable which is running the loop. So it will start from 1 to 4, and when we if we don't specify the gap, MATLAB automatically assumes it as 1 colon 1 colon n cases. If this is not specified, it automatically is 1. So this will solve it for IC is equals to 1, 2, 3, and 4. So when IC is equals to 1, where AZ naught is cases 1, 1, elevation is also cases 1, 1, label is also, sorry, the elevation is 1, 2, label is 1, 3, and description is 1, 4. So what is AZ naught 1, 1? AZ naught 1, 1 is 0. L naught is 1, 2. This will be 90. Label is 1, 3, broadside, and description is 1, 4, beam along plus Z. So we have we have extracted the first case over here, and now let's run the script for the broadside case. So this will solve for the broadside case now. So we saw the function earlier, which was the make phase. So we'll call the make phase function now. So we don't have to keep, so we are solving this inside the loop, and we don't want to, write a very long loop function, write a very long loop. So what we do is we call functions. So, so what will this do is this will send the value of send the size of the array, uh, the wave number, the spacings, the azimuth and elevation angles, which it extracted now for the first case. And then if you recall, the make phase function returns the phase map, and that phase map is saved in the phase degrees. Next, we also just calculate the bx, beta x, and beta y in degrees. This is for plotting. So we don't actually need this for solving. This is just for plot. And then we build the array. And to build the array, we call the build array function, which we saw before the phase map. So build array will send the element, which we had defined way earlier as a dipole, the size of the array, the spacing, and the phase map we just called. So we called the phase map and then sent the phase map into the build array function. And the build array function will create the array and send that to ARR. And this ARR, we can plot this. So plot of to plot an array or an antenna in the MATLAB, you just use show, and this will bring the structure on your screen. And then you can give the figure labels, titles, and everything that you need to make it look prettier. And similarly, inside the loop, we'll also plot the phase excitation map and the radiation pattern. I didn't have enough space in this slide, so I just wrote the instruction over here. In the next slide, we'll see how the phase excitation map and the 3D radiation pattern happens. So I'll stop here. I actually have talked a lot now, and I don't know if I give enough time to absorb. So maybe you can look at the script, and if there are questions on this, you can ask, or anything that we have just discussed. In the next slides, we'll cover the phase excitation map and the 3D radiation pattern, and then we'll be done with planar arrays. Um, So, am I audible now? And okay, I've asked two questions and okay, thank you. Okay. So I guess I'm audible and maybe there are no questions. Also, yeah, you'll need to run the script and go through that in detail because a lot of it is happening right now in the script. So maybe I should summarize up till now. So what we did was we defined parameters. After defining parameters, we defined the element, which is the dipole. After defining the element, we created a function. We created a function build array. Now build array took in different arguments and the phase map. So we also built a function called phase map, called make phase actually. Make phase. And make phase took in more arguments. And now we're solving it for different cases. So we are solving it for case 1 to 4. And each case, what we do is we get the parameter values. We get the parameter values, then send it to make phase. Make phase gives us the phase, and then we call build array. And build array gives us the array, and then we use show to get show the array, and then we build the phase excitation map, and then we plot the 3D radiation pattern by just using pattern function. Is this, as I guess this must be, this routine must be clear now. So how to build the phase excitation map? We use a function. We use this function property called image sc. Image sc basically takes in a matrix. So it will take, let's say, n cross n matrix and then plot it as an image on the screen as a 2D plot, right? And if you give it a 3D value, it probably can plot that as well. And then images will plot the phase excitation plot. You can have your X label, Y label, and then make it more beautiful with title and subtitles. And for the 3D radiation pattern, as always, like we have done before, uh, we'll use the pattern function, and the pattern function over here takes the array and the frequency at which you want the pattern, your 3D pattern. And you can include color bar, titles, uh, figure labels and things. So this is how we generate the geometry and the pattern. And for different, if you run it run the script for each case, let's say case one, case case two, case three, and case four. This will create the geometry by calling this will call build array. Build array will use make phase, which will create the phase map, and then we'll get this geometry. And then you can also you can plot using image SC of the phase map. You can get the script. You can get this plot. And then finally, if you use pattern on your object ARR, so your ARR saved in build array, and if you use pattern on ARR, this will create all these cases. So I'll pause here. If there are follow-up questions or any questions whatsoever on planar antenna design, you can ask now. So similar to this, we can also do different kinds of arrangements. So the first case we have already seen where we had z-directed dipoles, and by changing the phases, we were able to plot the beam in broadside, x direction, y direction, and 45 degrees. Similarly, what we can also do is have dipoles along the x axis and but still in the xy plane. So we have x directed dipoles in the xy plane. So this will look something like this. And in this case also you can have different phases. This will also result in this in this also if you use the phase map phi mn is equals to m beta x plus n beta y. The same concept, we can have an x directed, y directed, and tilted beam. And you can also do it again with y-directed dipoles. This is x-directed dipole, and this is z-directed dipole. In the xy plane, again, you can have in x direction, y direction, 45 degrees, and broadside. Right. So there are many possibilities. The script is also with you. I can run this script also, and so let us run this script. It's the same thing. If you go through the script, we have again the number of dipole, the length of the dipole, as I mentioned earlier, because if you have lambda by 2 spacing and your dipole is oriented in the same direction, this will overlap. Is there a question? So no questions. So again, so if you have dipoles, lambda by 2 spacing, and your dipole is also lambda by 2, and if you arrange them in the x, if they're in the x direction and they are in the xy plane, then they will start touching, like intersecting, and that creates a geometry problem. So, so what I've done is I've made the spacing factor 0.5, but the dipole length is 0.4. So that ensures that they do not intersect. Then again, we define the parameters, and this is for a fail safe, just to check if the other dipoles are overlapping. And then we create different cases for dipole configurations as Z dipole, X dipole, Y dipole, and in all these cases, the orientation, the tilt, how much, the degree of tilt, the tilt axis, and the description, and the different beam steering cases, 0, 90, 0, 0, 90, 0, 45, 45. And what we do is we do a nested loop. So the first case we tilt the dipole, and the in the inner loop, um, we uh, we we in the inner loop we build the element. Yeah. In the inner loop, we create one figure per beam case. So first we are changing the dipole orientation outside, and then inside we are also changing the beam cases, right? So if we run the script, and it's all very similar. We calculate the beta x, beta y values. We create the phase map. We then create a rectangular array like before, and then amplitude and phase shift. And phase shift is given by the phase map that we are calculating over here. So all this, and then we can run the script. So this will again take maybe a minute or two. Meanwhile, you can also look. So this in the script, you can always include the print command like this fprintf, and this will give you the location where your script is running right now. So it has done an overlap check, and now this is the geometry. So this is for the Z dipole. We have this is simulated case one, case two, case three, case four. Now it has simulated for X dipole for all the four cases, and now this has started simulating for Y dipole. It's now simulating case two. So you can include your print functions inside or display inside the script at different places just to keep track where your code is running. It's now complete, and it's creating three geometry plus 12 pattern figures. So if this was an earlier MATLAB version, then all the figures would pop up. If you do not use position in your figure, then this will, in the later MATLAB version, this will all, put it in tabs. What we can do is we can look at all of them together. We can go to layout and do tile all. And so it's plotting in a 16 cross 16 grid. So this is the geometry, and then these are the four patterns. Let me make it better. This way we have three cases, right? We have one, two, three geometries and four patterns each. Yeah. So I've arranged it in a 3 cross 5 uh, tile layout, and now we can also again see the geometry is same in all these cases. Sorry, no, in for the first case, the geometry remains the same. If you rotate this over here, you can see the geometry is same. And in these cases, the geometry is different, but the beam direction you can see it's again we have broadside, we have along X, along Y, and along Z. Yeah. And so this is the X-directed dipole. You can see this is they are along the X direction, and they are in the XY plane. Similarly, this is a Y-directed dipole. They are in the XY plane. Yeah, so the script is with you. Make sure you run them. And similarly, there is one another case that we can look at, which is the loop dipole combination. So in this case, what we can also do is we can have different types of antenna elements in one array. Let's say this is the pattern and the geometry. If you do a loop array for a 4 cross 4 element, and then we have already seen 8 cross 8 dipole array. We can have a 4 cross 4 dipole array, and then we can have them together as well. So loop and dipole together, and then this will I mean, this is a demonstration you can do with different elements and different arrangement, and this can help you with beam steering or higher gain in this in. So now you can, so we have a 4 cross 4 dipole, a 4 cross 4 loop, so that makes it 8 cross 8, but in a smaller dimension. And this will help with higher gain and beam steering. So the script again for this also is with you. This will be labeled as loop dipole array MATLAB. And in this case, one difference is that instead of using rectangular array, we are using a conformal array. And the conformal array will take the elements as a list. So repmat is basically create as a function from MATLAB, which was creating a list of different elements. Uh, this is taking the structure LP, which is the dipole, and then this is the number of rows, and this is the number of columns, and this is creating a list of different elements. Just, I'm sorry about the disturbance. Sorry about the disturbance. So we are using a conformal array. This takes the list of elements. The element position is again a list which has the position of different elements. And then again, it takes a reference and the amplitude and phase shifts. Uh, this is for the loop array. Similarly, for the dipole array also, this is again taking uh, the list of the elements, the position, the amplitude, and the phase. And then if you can combine them together, the loop and dipole together, this is again taking the two lists of the different types of elements. The position again for the the dipoles and the loops, and the position and the amplitude and phase. And if you run them together, run them, you will get all the plots too. So let me run this, and then we'll compare the patterns. So this is for the loop array. This is the pattern. This is the dipole array. This is the pattern, and this is the pattern for the loop and dipole together. And you can check the elements in the workspace. So if you look at pause and pause dual. So pause is basically storing the x, y, z coordinates of the element positions. So the first element will be at 0, 0, 0. Second element will be at 0, 0.5, and then 0, 0.1. So this is the coordinates of all the elements. And pause dual, since it has both loop and dipole. So this is the first up 1 to 16 is basically the positions of all the loops. And then again from 17 to 32, it's all positions of the dipole. So conformal array takes in the location of each element, and then you can give the list of the elements as well. So the first 16 elements are the loop, and the next 16 elements are the dipole, and then their respective locations, the amplitude and phase shifts of each element. So all of them as given as list. This is all for the planar arrays. Next we'll start with a Friis transmission demonstration. So if there are questions on planar arrays, you can uh, ask them now. If there are no questions, we'll proceed with the Friis transmission demonstration and then finally do MIMO simulations. And then that will be the end of this class and this course. Okay, so we'll start with Friis transmission demonstration. So this is pretty uh, straightforward. We have already seen the Friis formula and the antenna theory and microwave lectures. And this part of the lecture will just demonstrate how to, verify the Friis formula in the EM simulation space. So we'll implement the antenna simulations. We'll verify the Friis transmission equation, simulate the effect of distance on coupling and the polarization mismatch loss. So from our theory knowledge, we have seen the in the far field with the effect of the power reduces as a function of 1 upon r square, where r is the distance. So let's say we have a dipole over here, and at a distance r, the power at two particular position, this will reduce as a function of 1 by r square in the far field. In the near field, this is different. Because this results as an approximation of the E field expression. If you are plotting, this will have 1 by r square, 1 by r cube, 1 by r4. All these terms will be there. So based on the approximation of the distance from your antenna, different terms dominate, and that those effects are seen. So in the far field, it's 1 by r square. And then this is also dependent upon the polarization alignment. For example, if you have two dipole antenna and if they are aligned properly, and, it won't affect. But if they are, one of them is tilted like this and the other is tilted like this, yeah, so there is a as since the dipoles are linearly polarized, there won't be any communication between these two antennas, and this also affects depends upon the antenna gain. So the gain of the transmitter and gain of the receiver. So if either of them is bad, the receive power will be bad. Now, the Friis transmission equation can be rearranged to get the S parameter. So if you uh, bring this P transmitted below the PR, power received. So this is basically your H21. Sorry, this whole square is H21. So if you take the root all over, you get H21 is equals to root over gain of the transmitter, gain of the receiver, and lambda upon 4 pi r. R is the distance of separation between the two elements. And we'll run two experiments. The first is the effect of distance, and the second is the polarization mismatch. I have put animations to show you whose script I've shared. So the animations are based on just the analytical formula, and you're free to use it uh, as you wish. So this is the first case. As the distance of the antenna increases, your power received uh, reduces as 1 by r square. And I plotted this for three different frequencies at 2.4 gigahertz, 5.8 gigahertz, and 60 gigahertz. And you can see it also depends upon the frequency. In the expression, you had seen lambda was dependent upon the lambda, and lambda is 1 by frequency. So if you So if you increase the frequency, the C power also reduces. The next is the polarization. So your red dipole is your transmitter, blue dipole is your receiver, and the yellow line is the cos square, the cos component in the expression. So it is dependent upon the cos square theta. So let's play this. So the cos component becomes very small when the antenna is rotated to 90 degrees, so, and hence uh, the the C power drops significantly as cos square. And this plot over here was shows the polarization loss factor. So one thing is, so at 90 degrees, it's completely zero. If you start rotating again from 90 to 180, this will start increasing. So this will look the plot will become something like this. And then after 180 degrees, it will again start decreasing and something like, so this will, at nine, whenever the cos theta is zero, this falls sharply to a very small value. And this is what this the polarization pattern plot says. So at polarization loss factor, it's yeah, so it's maximum. The polarization loss factor is maximum at 90 degree, and so the polarization loss, so receive power is zero at 90 degrees, but it's maximum at 0 degrees, and then it's uh, zero at 270 degrees and so on. So this is what this pattern shows. So if you run the script again, uh, it becomes zero at 90 and 270 degrees. Now to do this, the previous plots were from analytic formulation. Now to do this using the EM simulation in MATLAB, this we again write this script, and it's a pretty straightforward script. Again, we'll be using the array functions from MATLAB. The and To do simple demonstrations, we'll use the linear array and then just manipulate the spacing. So first we define the simulation parameters, the frequency, the velocity of light, the wavelength, then the dipole length, dipole width, and the frequency range in which we want to see the results. And this particular over here is just to find the index of the frequency of interest. Let's say F naught is our frequency of interest. So we find the index of F naught in the frequency this frequency array. And then we define the distances at which we want to run the simulation: 0.5, 1, 2, 3, 5 meters, and the angles where we want to see the polarization, the S21 for the different polarization. So we are running from 0 to 90 degrees with 10 degrees steps. For the distance simulation, first we define an S21 matrix with zero, which is just zeros for for the frequency, the number of frequency that we want, and then the different lengths. So this will define a matrix of for each length. Let's say 0.5, 1, 2, 3, 5 meters. It will define S as S21 as zeros. And then once we simulate, we'll fill up these values. So we're just initializing it over here. And then for different distances, we run the EM simulation. So we had created a list of different distances: 0.5, 1, 2, 3, 5. So, so that was 1, 2, 3, 4, 5, 5 values. This loop will run 5 times for different distances. We're just printing it over here. We're starting a timer just to see how long it takes to run the simulation. The tick and talk gives calculates the time difference. So you can ignore this thing over here. And if you, any part of the code that you think is taking longer, you can use this actually, take and talk. And then we create the dipole element as with dipole length, dipole width. And then we create a pair with linear array using this dipole. We to run our simulation, we saw we needed two dipoles and separated by some distance. So let's say the distance is di over here, and di at diff so distance, and di is our loop variable, and di, when di is equal to 1, distance is at one position is 0.5, so this will take 0.5 as the gap between the two elements. And then we calculate the s parameters by using this the array element that we created, and the frequency steps that we created using in the previous slide. So we get the S parameters, we just extract the S21 over here, and and that's it. Now we get the S21. And now to analytically get the, the S parameter, the S21 from the Friis expression, we get the gain values for the antenna. And since transmit and receive antennas are identical, we say we get the gain for both the antennas. And using the Friis expression, root over GTGR into lambda upon 4 pi distance d, we get the S21 from the Friis expression. And then we can plot this. So you can see for different distances, for 0.5 to 5 meters, if for very small distance, your S21 was better. And if you keep increasing the distance, the S21 reduces, which is also the coupling between the two elements. And again, if you get these values, the S21 values from the EM simulation and the this expression, they match very closely. Right. So this is the distance simulation results. I'll pause over here if there are questions on this. In the next slide, we start with the effect of polarization on polarization of the antenna on the receive power or the S21. Okay, so we'll proceed. So in the next slide, we have polarization simulations. So similar to the previous case, we initialize the S21 matrix. And now we fix the distance of, in this case, because we are now rotating the dipole, starting with, uh, 0 degree, 0 degree orientation, right? Yes, from 0 degree to 90 degree, we want to go, and in steps of 10 degrees. So we'll use the number of angles. So we have 0 to 90 degrees in steps of 10. I guess that's 10 or 9 or 10 simulations. And for each degree, each rotation will this loop will run. And in this case, we create a transmit and receive dipole with the same specifications. But the received dipole is tilted by AI uh, angles at AI, and AI angles is um, the first case it's 0 degree, next is 10 degrees. So angle one will be 0 degree, angles two will be in 10 degree, and so on. So for each iteration of the loop, this tilt angle will change, but the tilt axis remains same, and it's rotating at, from the y-axis. And then we create the simulation space using conformal array. And its object is ARR. And the conformal array takes the list of the elements. So we have a transmit and a receive. And the element positions are given by one is at the origin, the other is at 3 meters away from the origin and the x direction. And then once we have created the conformal array, the simulation space, we use this S parameter function with 50 ohm normalization and the frequencies on which we want the S parameters. We extract the H21 for each rotation. So we save it for each rotation. We save the S21, and similarly, we also get we, we calculate the loss from the EM simulation. So at 0 degree, which is at the first position, we have the maximum transmission. So for one, this will be zero. We will have the lowest loss, and then if we for rest of the other degrees rotation, we will save the losses, and we'll also calculate the loss from the Friis expression, which is 20 log of cosine of angles, and then we can plot this. So if you can compare the analytical expression also, uh, at for 0 degree rotation, we had the maximum transmission, so there was no loss, and then this loss increases rapidly as the function of cos square theta. And the S21 also, it uh, reduces drastically if we move to 90 degrees. So this is the Friis transmission and for distance and polarization. And then there are scripts on the plots. So I won't go through the scripts of the plots because we have already seen how to plot in different case in the previous slides. So it's all plot, hold on, plot, X label, Y label, legends, X text, and then including markers over here, and then title, subtitle. So it's pretty straightforward. The key takeaways, we verified these three cases. We saw the effect of distance, polarization, and the gain. The gain was same in both the cases, and we saw the effect of lambda as well in terms of frequency in the earlier videos that I showed. So before we move on to MIMO antennas, I'll just stop here and uh, wait for questions if there are any, or anyways, we should maybe take a breath. We have covered uh, two topics. The first was the planar arrays, and the next was Friis transmission. Uh, bo- uh, uh, Both these use the array functions, the rectangular array, the linear array, the conformal array available with MATLAB. Antenna toolbox. And next, we'll look at MIMO antenna simulations, and then we'll end the class. So there's a question that S21 is automatically calculated by built-in function in MATLAB. Yes. So you have the function called S parameters. Okay, I have not run this script, right? So maybe I should run this script and also discuss the question. Um, there is this function called this is S parameters, right? And this takes in the object that you're giving it. So once we create the array or antenna element, a single antenna. Yeah, so the question is only for array antennas or any single antenna. So it takes in any geometry, either array or single antenna element that you create the object, you give it to the S parameter function and the frequency points where you want to get the S parameters. So this frequency, if you check, this frequency is defined from 2 gigahertz to 3 gigahertz for 21 points. So all the 21 points, this will solve the S parameters. So where did I lose it? Yeah. So this will so you give the frequency values where you want the S parameters. You give the structure, the object of the array or the element and the impedance normalization for the S parameters, and call this function S parameters, and this will give you the S parameters as this object. And within this object, there are multiple things. So if I run this, just give me a second. It's running for all the distances and now for all the polarization angles. We'll come back to the plots. So let me open the S over here. So the S parameter function will return this particular structure. This will have impedance, the number of ports, the parameters, and the frequencies. So if you open this parameters, this will be a complex value. But to read this value, you need to extract the parameters. So what you do is you do this in the script. You squeeze the parameters of the S function, sorry, the S object, the S object's parameters over here, and you squeeze the to one and all the S parameter value, and just take the absolute, just to get the magnitude, you take the absolute and this to change it to dB scale, and then you save it. So, and it can do it for the elements or the arrays, whatever structure that you're creating, as long as it is an object of the MATLAB antenna toolbox, this will do it. If there are multiple ports, this will give you an S matrix of all, it will calculate all these parameters. And if there is just one antenna element, so it means it will have only one port, it will only have S11 stored in it. Uh, I hope I was able to answer your question, Mohammed. If you have any follow-up questions on this, meanwhile, I'll look at the results with you. So after running this particular script, you will see something like this. You'll have the distance effect on the coupling, the validation of the Friis expression, and then the S parameters with the polarization, with changing polarization, and the verification of EM versus Friis theory, and the polarization pattern again. For 90 degrees, you will have no almost very low S21, but then at for 0 degree rotation, you will have the maximum S21. So that's what it is shown in this polarization pattern. Okay, if there are any follow-up questions before we start discussions on MIMO antennas. Okay, so we are um, in the last topic of this course, the MIMO antennas. There was a request in the first class to cover this, so let's do this as well. So the goals we will for every MIMO antenna paper that you'll go through. This is the typical part, uh, typical structure. They'll first design the single element, and then you'll see the performance of the single element, and then they build the MIMO antenna system, and then you have different MIMO metrics such as envelope correlation coefficient, um, maybe total active reflection coefficient, channel capacity loss, or diversity gain, which is calculated from envelope correlation coefficient. So these are the different metrics. I won't deal with the the importance of these metrics because I'm not exactly a MIMO antenna expert here. I do have the definitions written and the formulas, so we'll be using the the formulas and the expressions on how to get these parameters which are popular among the MIMO antenna designers. So if you make an antenna, MIMO antenna, and so that you can calculate all these parameters. And these parameters are along with the S parameters. So S parameters are also must. So what is MIMO? MIMO is multiple input, multiple output. So there are more than one ports in the antenna system. And instead of having just one transmitter and one receiver, we use multiple transmitters and multiple receivers in the system. And the benefits include higher data rate, diversity gain, improved reliability, and is frequently used in your Wi-Fi, 5G, radar, and satellite links. You must have seen your Wi-Fi routers. They have multiple transmitters there. And then your mobile phones may also have multiple receivers to increase the performance of your communication link. So a typical MIMO antenna layout is just the different antenna elements. They might be the same element, or they might be different types of elements arranged together in some spatial way. For our case, we'll use a very simple case to demonstrate. This will we have in the examples we'll have four elements. Um, the main example that we'll discuss is the dipole. So we have four dipoles arranged in a box way. We could also have them in just in one line like we saw in the arrays, but let's change the of geometry, and we have arranged them in four corners of this cube. And this also ensures that there is more spacing between different elements, which increases, the isolation between the elements. The isolation is also directly dependent upon the distance. So if you have more spacing between the elements, you will have more isolation. So, and the spacing over here is lambda by 2 between these elements. You can lambda by 2 spacing is known to reduce coupling. But you can also play around with these parameters. This will avoid creating loops and most common in MIMO designs. But again, this is very old knowledge, and there are recent papers doing a lot of things. So we'll first look at the dipole, and then we will look at bow tie. So there was also feedback that I should cover different types of antenna. So I've included bow tie, and then there's also PFA, which is folded dipole. Sorry, which is inverted F. Yeah, right. So something like that. I've included them as well. So this is this. So we have already done single element analysis in the first lecture for the dipole, where we introduced a dipole, and then we plotted the S parameter. We got good enough matching. We also saw that since this is close to 33 ohms at resonance, so this will only match up to minus 14 dB. So that's pretty okay over here. And then we also plotted the impedance and the radiation pattern. It looks like a donut or a vada. And at the resonance is decided when your reactance becomes zero, and your impedance at that value gives you the input impedance of the antenna. So this comes out to about 73 ohms. And once we have the single element, let's jump into the four element MIMO. You can always keep on increasing this. Just make sure you do not run out of memory in your system. So the spacing is dx dy, which is lambda by 2. And now to create a MIMO, will use conformal array. And how does conformal array work? The conformal array takes in the element that you want to give it, whose array that you want. So the element will take in a list of different types of the elements that you want. Since in this case we want them to be identical, so we will just use LM, which is a dipole antenna, and we want let's say four of these. So we'll have four of these over here, n equal to 4. And then for each of these elements, we have to specify its position. So the first dipole will be at minus lambda by 2, sorry, minus lambda by 4, and minus lambda by 4, dx by 2, dy by 2. So this is over here. And then the next element is at these locations. So this is somewhere here, here, and so we have specified the x, y, z coordinates of each of the dipoles and give them as a list. So this will create a map. So each of these element is a dipole, and then I've given the position. Pos 1 will specify this, pos 2 will specify this, pos 3 will specify this, and pos 4 will specify this. Suppose we have specified the position of each element. We have given the element. The reference is given as origin. You can move it as well. And then each element is given the same amplitude, and there is zero phase shifts among the antenna elements. And then you can use we have created this conformal array object as MIMO, and then you can use show MIMO to show the structure over here. You can include a title, which will come over here. You can also include a subtitle, which will come over here, and put draw now. It will create this figure. Next, um, to get the S parameters, so MIMO, since this MIMO structure has 4 ports, we will have an S matrix, which will be 4 cross 4. And this will have S11 to S44. And this is the S matrix look like. And your S11 or your SII gives you the return loss at your ith port, and your Sij gives you the coupling between the ith and jth port. Right. So what for the target would be to have good return loss and low coupling. So we don't want coupling between the MIMO elements, which is a bad thing in MIMO antenna design. And so if you run this particular script that I've shared, you'll see the matching is somewhat okay-ish. It's not best tuned. You can see it's barely around -10. And the resonance is a bit shifted. And the matching, the although this your coupling between your S21, S31, this is below -10, but it's recommended your match your coupling be below -20 actually, at least in these cases. And there are papers going up to -40 dB as well. So if you do a better design, you'll get it. But for demonstration purposes, we'll use a dipole. And in this particular case, it's very hard to, match the dipole below -14 and then again improve the isolation because of the geometry that dipole has. Now, to get the S parameters, it's the same thing. You lay out the frequencies where you want, starting from 4.5 to 7 gigahertz. Our target is 5.8 gigahertz now, and we are using 30 points. And then you print all these things. You start the timer just to see how long it takes to simulate. Then you call the S parameters. You give the MIMO that you have created and the frequency sweep where you want to sweep get the S parameters, and you say get the S parameters as S. Now you can get the frequency access from S dot frequencies, the number of frequency values as from over here, and then the magnitude of the S parameters as S mag, and find out the location of your resonance as F axis minus F naught. This gives you the index of the resonance index of your intended F naught frequency. And then you can plot the S parameters. You can plot the S parameter value at F naught by just using this index. You get S21 at F naught, S31 at F naught, S41 at F naught. And similarly, S1112, S11223344 at F naught. So this particular part, F printf, actually plots this in your command window. So it will first plot computing 4 cross 4 at 30 points. Then it will give you T naught as tick. So this will plot your simulation is started at this when you calculated, sorry, but started the timer here, and your talk should be somewhere. Yeah, talk is over here. So this will TikTok will give you the start time, the finish time. So it took a total of 1.4 seconds, and then this if print part gives you the S parameter values at 5.8 gigahertz. So you can see it's all above 10 minus 10 dB, which is bad. We need it uh, below minus 10 at least. So there is some tuning to be done here. And then your coupling values are also not good. S41 is okay, but then again, S41 and 4 are separated pretty far probably. And 21 and 31 is not good. Now to plot the S parameters in window, in the previous part, we just plotted the values in the command window plot. Yeah, but you have already calculated the S parameters. Now you can just plot the f-axis and the magnitude of the s parameters by using plot function. And since you have 4 into 4 16 s parameter values, and most of them, since this is a reciprocal circuit, a lot of them will resemble the same. So you can see S1, 1, 2, 2, 3, 3, and 4, 4, they have the same plot. And similarly, S2, 1, 1, 2, 3, 1, 1, 3, 2, 3, all of these will have also the similar plots. So what you can do is not plot all of them, plot some selected ones, and you can just plot the 1, 1, all the IS return losses by using this particular part of the script where you just plot II values here, and then you can plot the pairs as 1, 2, uh, sorry, 2, 1, 3, 1 like this over here. Or what you can do is just plot all of them. It's up to you. And then you can have these markers and things which are there in the script, how to do it. Don't worry about these two. This is just to return for return loss. We're using blue, red, green, magenta as the colors, and B dash dash gives you a dashed line. So blue dash line, red dash line, green dash line. So that's what is specified over here, just to make the figures choose the colors that we want. And then title, X label, Y label, legends. It's all up to you how you want to do, how you want to make this prettier. So that's how we get the S parameters. Maybe before I move to other MIMO parameters that we usually tend to look at, are there any questions on the MIMO antenna creation and the S parameters display using the MATLAB antenna toolbox? Okay, so we have covered MIMO antenna design, and MIMO antenna design we used conformal array to create the the MIMO geometry, and then we again simply used S parameters function uh, on the MIMO to get the S parameters. Next, to get ECC and other metrics, we don't have functions, so we'll have to write the formulas and get them. So let's look at the formulas first. So the ECC is a measure of correlation between the antenna signals. So if the and the general trend is if the ECC is below zero point 0.5, it is acceptable. And if it is below zero point 0.1, it is excellent. And what is it? It is expected that a low ECC is better for MIMO diversity. Zero is for perfectly independent antennas, and one is for identical antennas. So if you, it means all your antennas are listening the same thing. So there is no diversity uh, in the signals that you're receiving. So it is essentially means that you were better with just one antenna. But if you have, so if you, for example, if you install four antennas, but you get the signal which one single antenna could have done, it's probably useless. Your MIMO is not working. But if your four different antennas are helping you in some way, then it's better. If it is improving your some functionality. So the ECC is calculated from the S matrix. So once we have already seen how to get the S matrix. Now we need to just extract the individual S matrix values, SKI, SKJ, from K running from 1 to n. And then similarly, yeah, on the denominator as well, and we take the ratio and get the ECC. So we have the formula, and we just need to implement this formula inside MATLAB after getting these parameters. And once we have the ECC, we can calculate the directive gain and diversity gain. Your diversity gain measures how much your signal reliability improves when multiple antennas are used. It's another metric just derived from ECC. So it just tells you if you have more than one antenna, is this has the signal reliability improved? It's a metric. You can go deeper into the meanings of this um, through literature, and the goal is to have a higher directivity gain, more than 9.5 dB. So if you have a low ECC, your diversity gain will be higher, right? And it's, as the name suggests, it is a gain, and gain should always be higher. A higher diversity gain means a stronger signal reliability. And the next parameter, which is seen in papers, is the total active reflection coefficient, which is again calculated from the S matrix and multiplied by the excitation vector, which is given something like this. And this measures the reflection when multiple ports are excited simultaneously. So um, yeah, since you have many antennas in proximity, you might also get reflections from the other ports, and this measures that. And finally, you have the channel capacity loss, which measures how much channel capacity is lost due to antenna correlation and mismatch. So in this case, for channel capacity loss, it's highly dependent upon the isolation of the antennas. So if you don't have good isolation, you'll lose channel capacity. And this is calculated using the second log of the determinant uh, of the matrix of this determinant. And the target is usually less than 0.4 bits per second per hertz, and the lower is the better. Now, let's not worry about what these means. The focus is on how to get these values through the script. So CCL is calculated by this formula, but for this we need the determinant of the psi, and psi is now calculated by using these two expressions, and then both of these are again calculated from the S matrix. So now, since we have already calculated the S matrix, we can easily calculate all the four metrics that we need for evaluating the performance of the MIMO antenna. So how to compute these? So I've listed the formulas over here: ECC, diversity gain, TRC, and CCL, and the parameters that are needed to calculate these. So we first initialize the variables to store them: ECC, DG, TRC, and CCL. Then to calculate ECC, we have summation over here. We have again summation over here, summation over here. So we need to run a loop starting from 1 to n for all these cases. And and again, we need to also extract the S parameters as we need the S parameter matrix. So what we do is we get store the S parameters at and we also need to solve this for all the frequencies, right? So the outer loop runs for all the frequencies, the number of frequencies, and then inside the first outer loop, we extract the S parameter matrix at each frequency. At each frequency, we are extracting the S matrix, and for each frequency, we calculate the numerator, the denominator, and once we have the numerator and denominator, we divide the numerator by the uh, denominator, and then we get the ECC value. So we have got the ECC from this loop. And once we have the ECC, we just take the 10 square root of the ECC value, we get the directivity gain. And to get, we define this parameter A is equals to root over n one and this one's matrix. So we define A and then we can calculate it TRC by doing the root over of summation of the S matrix and A. So we multiply the S matrix with A and then do a summation of all its elements and do a square root. And this gives us the TRC. And then finally, to get the channel capacity loss, we first define the I means an matrix, a unitary matrix like this. And then for to get the psi values, we have to run again summation from 1 to n, 1 to n. So we do that. We run this loop from 1 to n and 1 to n. We calculate the psi values for both the cases for ii and ij. And then we can calculate the CCL by just taking a log of the determinant of psi. We get the CCL values, we can print them, and this will print this MIMO matrix at 5.8 gigahertz in your command window as ECC. This is less than 0, this is greater than 0, which is good. TRC is less than 10, which is also good, but the CCL is not good because your dipole does not have very good uh, diversity, very good isolation between different the elements. So the CCL is bad. But if you make different designs, you might have improved CCL performance. Now you can similarly, once you have all these values, you can just use plot and uh, use squeeze function on ECC TRC and plot these values. You just use plot and you can get these parameters. So let me go through the plots again. So once we have run this, you can see your ECC 1, 2, 1, 3, 1, 4, 2, 3 are solved for over here. And all of them are pretty low, below 0.1, and the target was 0.5. For diversity gain, the target was 9.5 dB, and there are all close to 9.9 dB for the different ports. And your TRC is also pretty good, and your channel capacity loss is not good. This is above the required target. Okay, so before we move on to a different design, let's run the script. We have seen the script already. So this is the script that we were looking at. We, we define all the all the variables over here. Then we create the element dipole. We show the geometry. We get the S parameters of the single element over here. We plot the impedance of the single element. We plot the pattern of the single element. And then we move on to the MIMO geometry, where we have seen this, how we create geometry. We uh, define the spacing between them. Then we make a list of the location of the different elements. Then we use conformal array, give them the list of the elements, list of the position, the amplitude, the phase shift, the reference, and then we use show. And the MIMO was the element that we created over here using LM. So we use show MIMO. Then for the S parameters, we just use the function S parameters, get the frequency, number of frequency points, the magnitude of the S parameters, and the location of the index of the F naught frequency. We plot the S parameters at um, and then we plot the S parameters at S11, uh, 2233, those values, and the coupling between 2, 3, 4, 2, 2, 1, 3, 1, 4, 1. You can do it for all the S parameter values. And then we plot the S parameters by you just using the plot function. Moving on to the MIMO metrics, we first define the variables. The numerator and the denominator, which had summation upon them. So the summations were from 1 to n, 1 to n. So we are using for loops to run those summations. And then the diversity gain can be calculated from the ECC. TRC is calculated using the S matrix and this excitation function matrix. We multiply them, get the TRC, and then finally for CCL we calculate the psi functions and then the expression that we had, and we can plot them, and then we can just print the values at the F naught frequency. We can also plot them. So the plot functions are here. And let me run the script. So there's a question, or can I explain the CCL more? And I would say I cannot, probably because I'm also not very confident with this metric. So the CCL is the channel capacity loss, which essentially means how much the channel capacity is lost due to antenna correlation and mismatch. So all the metrics that we saw before, the ECC, PARC, and DG, they are all calculated between different ports. So you will have ECC11, ECC12, and all these things, TRC11, 12. So these metrics gives you the performance between two ports. Now channel capacity loss gives you the performance of the entire MIMO antenna or together. So it takes in the effects of the antenna correlation, which comes from the ECC, and mismatch, which is sort of reflected in the TRC. And altogether, if your MIMO antenna is working good or not is given by the channel capacity loss. So if you have poor matching, or if you have low isolation between the antenna elements, CCL measures this, and it's a metric defined to give the performance. And it is calculated by using it is calculated by uh, from the correlation matrix, and the correlation matrix is defined um, with this. Your correlation matrix is defined as these by using the psi values, and then you take the determinant of this, and then you get this CCL. More on this, I would request you to please refer to some better textbook who can explain this better. I too myself have never used this metric before. So I'm not confident on the importance of this thing. But I do know that recent papers are calculating this to show the performance. So I'm showing you how to do this if you're using MATLAB for this or for a project. Okay, so coming back to the simulation, let's run this code. And In the recent codes that I've shared, there will be a section which will be commented, and this will maybe written as load and replot. So I realized that some of these simulations, for example, with the patch antenna simulations or horn antenna simulations, they take longer and they take a lot of memory, and you don't actually have to run these simulations again and again. You can save the workspace and the replot them later. So I've included the script. So once you have run the script before, what you can do is uncomment the section and just run this section. Don't run the entire script. Click on the run section, and this will replot all the results that you already had. You don't have to keep running them again and again. Okay, so let's run the MIMO dipole. And yeah, so it's simulate plotting single element patterns. It's pretty quick, the dipole simulation. MIMO, as you keep on increasing the number of elements, it will become faster or slower. It's If you have a later version of MATLAB, you can do a tile all over here and you can look at all the results all together. Your single element, your performance of the single elements over here, and then your MIMO configuration, the S parameters, ECC, DG, TRC, and CCL. You can plot all of them. Similarly, I have also shared scripts for MIMO, PIFA, and bowtie. So let's run the bowtie simulation. It's the same thing. For bowtie, what you do is instead of creating the element as um, dipole, what you do is you design a bow tie triangular, and this is how you do it. You can use the design function and bow tie triangular and just give the excitation frequency. And if you want to tweak the designs of your bow tie, then you have to go into the function, the class bow tie triangular, and see what specifications that you are allowed to change. Just we can run the bow tie. So the bow tie will look something like this. And this will again plot all the metrics that we did for uh, dipole. We can look at all the results together. So this is a single element bow tie. Its matching is okay. It can be better. Its impedance is as it's not the best matched over here, but it's you can see the impedance is close to 50 somewhere here. Maybe this is 30 over here. So impedance will be fine. The pattern resembles a dipole. And then you can see again, since the orientations over here and the isolation is not good, if the isolation is below -20, your all these performance will also improve. The channel capacity loss is not good, but rest of them are satisfactory as per the convention. We just change the element over here and nothing else. So after this, all the script is same. It is running the same script. So if you just change the element, you're good to go for your uh, your MIMO script. So all this thing is same. All this script except line number 33. The script remains the same. Similarly, if you want to do PIFA antenna, you can you have the script with you. It will create a PIFA antenna like this, single element. This is a bit slower than the dipole, but still fast. So since the individual simulation is a bit slower, the MIMO simulation will be uh, even more slower than compared to dipole, but still doable on a regular system. And mind you, even in HFSS or CST, MIMO antennas are a bit slower as compared to single element because obviously you have a bigger structure at the same frequency, so you need more mesh information. So it's the same for over here as well. And MATLAB is pretty new in the antenna simulation space, so maybe over time this will also become faster for all the different cases. The good thing is you have all these presets which you can directly use. Just call the dipole or PIFA or whatever function, and this automatically creates the antenna. And you're also allowed to optimize based on the available geometry specs that they have. So while it's simulating, let me switch to the slides and just show you the plots. So for the bow tie MIMO, we had something like this. You had the geometry, you had the matching, your input impedance plots, the radiation pattern, and then the MIMO specs. So the geometry, the S parameters for all the boards, the ECC, diversity gain, TRC, and CCL. And then for PIFA, this is something you will get now. The single element looks like this. Your feed over here, this is folded F, something like this, inverted F. And then the resonance is okay. The impedance is fine. The radiation pattern looks something like this. We'll see in these once we are able to simulate the results. And then your S parameters and MIMO metrics are also over here. So you can see IFA performs a little better than the others in terms of the CCL, but still not good. Maybe you can play with the orientation of these elements, and this will probably meet the criteria. And then I've also shared the script for the microstrip patch. I won't run it now because this takes time. But you have the script. Run it and maybe go for a dinner and come back. You'll have the plots. Uh, and for the patch, you just have two elements on the substrate, and the matching is okay. And you can also plot the radiation pattern. The scripts I shared, you can also plot the radiation patterns for the MIMO antennas when I when when single elements are excited or all the elements are excited all at once. You can do that. So for the microstrip patch, if when each of the elements are excited, this is there's slight change in the pattern, and if both of them are excited, you will get something like this. So these results also correlate with the array that we have studied, and so that's all the results that I have to share. We'll just look at the you know the PIFA results, and then take questions regarding the course logistics. So any question that you have throughout the course, you can ask, uh, and then we can end this course. Any questions on class logistics? Any feedback that you want to share, or questions on the certificate? I've already informed. Please do fill up the feedback form if you need the certificate, or if you want to share your feedback. The scripts are with you. If you are missing any material, please post in the group. All the recordings are already shared for the previous three classes. This today's class I'll share again. Yeah. So you can see this CCL is much better for this particular antenna, and we have all the plots now. So you can see the individual geometry. This is the individual element. Um, this is the array. You can go through papers on how to improve isolation between the elements. See, the matching is better, isolation is better. So if your isolation was below -20, your CCL would definitely improve. And then your ECC diversity gain, see, this is close to 10, which is very good. And TRC is also uh, uh, it's it's okay. This could also be better. Yeah, so this is the results for this element, this FIFA and antenna and its MIMO. So there's a question: can we get this neatly arranged plots in MATLAB online? Good question. I think so. Yes. Let me run this script in. Not no. Let's do the dipole. Let's see if we can do it. Um, I should have MATLAB online open. How do I move this? Okay, let's run this. Let's say this is dipole MIMO. It's created a single dipole geometry here. Oh, okay. So this is actually creating multiple plots. Hmm. So this did not do as expected. Okay, maybe there is one way. Let me, where is the first plot? Let's start by docking this pole over here. So let's do it randomly now. If we dock all these here inside, so if I dock all the plots, it comes over here. Can I arrange this in a tile? If I do undock figures, okay, yeah, you can do it in the MATLAB online. You can maybe tile all. There were 10 plots, right? So I'll maybe do this. So this is too many. Okay, tile all. Yeah, you can do it. So what you had to do was you had to first dock all the figures together, and then do the arrangement. So let's say if let me just undock figure one. You have this floating figure here with you. If you click on this, this is a dock option. If you can dock this, so it will automatically dock it over here somewhere, and then you can tile them. Um, Kranti, did you follow what I did over here?
Yes, sir. I'm Giridhar. I have followed it. I actually got it very well.
Yeah, thanks. Okay, so yeah, you can play around the interface. And there is question, is there an advantage in using MATLAB to simulate MIMO antenna rather than using HFSS or CST? They provide GUI. Yeah, true. So MATLAB is, and this reminds me, I forgot to actually do the GUI based simulations. MATLAB also has GUI. For MIMO, I don't think it has. So let me just first do the GUI simulation and see if that answers something. So if you go to apps in MATLAB, and you have to look for the RF and mix signal. So it will have all these GUI based things. So I'll show antenna designer over here. So if you click on antenna designer, it should open. It's a bit slow in that sense. Yeah. So it's up. So see if you open the MATLAB's antenna designer, you can also look for the script online. If you can just go to the command window and write my antenna designer. This will open. Okay. So this blank space has opened. you can click on new, and then you get you have these options. So it's by default showing dipole. You can click on folded dipole, so it will create a folded dipole. And here is all the presets that you have. So let's say if you want to do a horn antenna, a ridged horn, let's say. So this it has created a ridged horn, and then since this will be all metal right now, you can say the design frequency as 77 um, gigahertz, and then click on accept. So this will create a horn antenna, and here is all the specs. So this is automatically calculated. You can also change them, and then you can change the material also. Let's say instead of doing a PEC, let me make it copper. So it will give these elements, and then click on apply. So this has changed to copper, and you can see the feed location is somewhere here. If you zoom in, you will see the feed location here. So it has created the horn. And now you can look at the frequency range. So it is simulated from 69.3 to 87.4 with a 0.77 um, 0.77 gigahertz steps. So what you can do is you can just click on the S parameters, and then it will start simulating the S parameters. I'm not sure if these are too many steps. Yeah, so it's has built the geometry, it has created the mesh. Now it will solve for 21 frequency points. Let's see if this takes too long, we'll cancel and do a simpler geometry. You can do this on, let it run, and you can also do this in the MATLAB online also. You can go to apps again, the same thing, antenna designer. Horn antenna is taking time, so let me just quickly simulate a simpler structure. Let's say a simple rounded bow tie at 5.8 gigahertz. Right, so this looks fine. Let me apply this and solve for the S parameter. So it quickly solves the S parameters and gives it to you. You can also click on the impedance. It will give you the impedance. You can plot the current on the bow tie. You plot the 3D pattern, azimuthal pattern, the elevation pattern. You can tile all the results together. You can also plot the mesh. So it will give you the mesh on the design. So it's pretty fast for just metals and smaller structures. Yeah, so it's taking longer for the horn. Maybe it's too big of a simulation right now. So it has done one frequency point now. So this will take some time. Let me cancel this for now. You can also do antenna array simulation. You can save this as some file. There is also option to optimize, which I have not explored. I'll request if you guys can explore and share your uh, experience, and then you can minimize this antenna designer as here. And you can also go to okay, before I move to array designer, you can also export this as a script. Export to workspace, then it will save all the S parameters, all the values, and you can plot it. You can also export it as a script. If you do that, this will export as script, and you see it will create an untitled 2 file over here. So this has created a bow tie rounded antenna, and all the specs that we gave it, and it's over here. Once you have the script, you can run this script also. Go to editor and run this script, and this just say um, bow tie from antenna designer. And you can run this, and this will again plot the results. Plot this as well. And then you can undock figures and arrange this in. You can so the this is the good part. So you can plot. What you can do is you can use the antenna designer, and once you are satisfied with your design, you can export it as a script. And then once you have the script, you can do much more with the script. So you can also plot VSWR and all the other functions which are not in the antenna designer. Or if you want to edit the properties, you have the script with you. Now you can also go to the apps and go to the antenna array designer. So this will also open. Hopefully, MATLAB will soon also launch something for meta surfaces. So you can go to array designer, click on new. You can select the orientation. Do you want it linear, rectangular, circular? You can do an infinite or conformal. So let's say we want to do a rectangular array. Um, we want it for rounded uh, dipole. So this is showing you the orientation of the element and the array. You can choose the frequency, let's say 5.8 gigahertz, and then we can select accept. And this is showing you the array positions, and this is the array and the layout in 3D. Once this is acceptable to you, there are also you can change the, let's say, metal to copper and other things, the element specifications and everything. You can click on apply. This will change it to copper. See, this is copper now. And then you can run it to get the S parameter. So this sort of also acts as a MIMO antenna designer. So you're getting the S parameters for all the four ports. So if you instead of making it as an array, connecting it all the antennas to one particular feed. If you use individual feeds, this gives you the MIMO results. You have the layout antenna layout with you, and then you can also do 3D pattern. So this will create the 3D pattern at your 5.8 gigahertz. You can do azimuthal patterns, E-plane pattern, impedance plots. So this is available with you. You can also do correlation. So I'm not sure how to do this. Maybe there must be a tutorial on this. And then again, you can um, tile. You can tile them all. And also export them as script or to your workspace. Once you've exported them as script, you'll get this script over here, and you can independently, run this. Just go to the editor over here, and you can run this as bowtie MIMO antenna designer. So you can run this, and it will again create all the plots that you just created using the array designer. So sort of everything, all the script that we learned in the class, you could also go to the apps and the antenna designer, array designer. There are other things to explore: transmission line designer, budget analyzer, PCB designer. You can run big scripts there. You can make it through GUI, and then get the script and then tweak on them. And the advantage of using MATLAB if is that you can use your own optimization codes, like methods, instead of relying on the ones available with just CST or HFSS. Over there also, obviously, you can include your own script. So yeah, so you can do that over there as well. It's much easier to do in MATLAB. It has its own environment, all the functions you can do it. And I've not included in this lecture, but you can also make your own designs. These are from the presets. You can also, mm, use shapes and make your own antenna design. You can go through the MATLAB's tutorial and help that will guide you. I've given you an introduction. And you can do that as well. It's just the one problem that I see with MATLAB right now is that it's really slow with dielectrics, so because uh, has some problem with its meshes. I guess they'll solve it soon, and then it's pretty easy to do a lot of things. And I did not show you, but you can use conformal in the MIMO design to place the elements also in at different locations. So I guess that's a whole to that would be another lecture in itself. But will this was meant to introduce everybody to a new or rather an old software, but with new features, which is the toolbox, and to introduce yourself to designs and things. Um, yeah, I showed you the GUI in MATLAB as well. So there is GUI. You can use that. Uh, there are some advantages, eh, but yeah, it's not as popular as HFSS or CST. So if you can try to use them, compare your based on your own efforts, which do you feel is better, faster, and yeah, do let us know. Any follow-up questions on this, Jay Vishnu? It was important to learn how the script works, so that even if you use a GUI, the GUI is limited as of now. I mean, it shows all the important parameters, but it does not, for example, for MIMO, even if you use the array designer, you cannot look at your ECC and other things. Yeah, obviously you can just save the S parameters and then plot them separately. But you can also do a lot more if you know the script. Yeah, thanks, Vishnu. Any more questions on the GUI based thing or antenna designer? Bhavna, is there a question from you? Bhavna, if you're asking a question, your audio is very low. Okay, so if there are no questions now, you can always reach out to me in the class WhatsApp group. I'll try to answer all of your questions. Make sure you fill up the feedback form. I'll share the class recording and the slides as soon as we end the class. And I will contact ISSS. I've not yet got the links from them to upload the slides on their portal. So if you've got those, you can access material from there as well. You already have the materials with you. Um, what else? The certificates, I'll try to provide you as soon as I can. I'll talk to them if whether they have an updated format. Yeah, that's it. Thank you everybody for joining this course. I hope this was helpful to you. And you can always reach out to me regarding any other topics that you have to discuss with me, either through WhatsApp or LinkedIn, or email. You have my contact with you. Thanks again. Thanks, everyone. If there are no questions, I'll Stop sharing the screen now and stop the recording. Okay, thank you everyone.